Welcome to our course on structural characterization of materials. I am Professor Ashutosh Tiwari from the Department of Material Science and Engineering at the University of Utah. In this course, we will focus on how we determine the structure of materials across multiple length scales, from atomic arrangements to microstructure, and how this structural information connects to material properties and performance. The first two lectures of this course are introductory. Their goal is to provide a broad, unifying overview of the major structural characterization techniques used in materials science. Rather than immediately diving into detailed theory or instrumentation, these two lectures will help you see the full landscape of characterization tools and understand how they complement one another. In the later lectures, we will return to each of these techniques, including electron microscopy, X-ray diffraction, spectroscopy, and scanning probe methods, and study them in much greater depth, focusing on theory, experimental practice, data interpretation, and limitations. Nanocharacterization methods fall broadly into two families, microscopy and spectroscopy. Microscopy reveals where atoms and features are. It resolves structure and morphology directly. Spectroscopy, in contrast, explains how atoms bond and how electrons interact with energy, giving chemical and electronic information. These two perspectives are complementary. Together, they connect structure to property. In this lecture, we will explore microscopy-based techniques such as XRD, SEM, TEM, AFM, and STM. In the next lecture, we will turn to spectroscopy and functional characterization, where light and particles reveal chemistry and bonding. We start our study with microscopy because it provides direct, spatially resolved information. Microscopy lets us see how atoms, grains, and interfaces are arranged, something no other technique can do so intuitively. It helps validate synthesis methods, determine particle size and morphology, and detect defects or inhomogeneities that influence properties. The next few slides will build from lower resolution, bulk averaged techniques like X-ray diffraction to higher resolution imaging tools such as SEM, TEM, and scanning probes. Each microscopy technique can be classified by the nature of its probe, whether we use photons, electrons, ions, or physical tips, and the kind of signal we detect. This framework helps us understand why different methods reach different resolutions and depths. As we progress through this course, keep these probe-signal relationships in mind. They explain both the strengths and the limitations of each tool. X-ray diffraction, or XRD, is the cornerstone of structural characterization. When a beam of X-rays impinges on a crystalline solid, the atoms act as scattering centers arranged in regular planes. Under specific geometric conditions, the scattered X-rays interfere constructively, producing strong diffracted beams. This condition is described by Bragg's law, 2d sine theta equal to n lambda, where d is the interplanar spacing, theta the diffraction angle, and lambda the wavelength of X-ray. By measuring the angles and intensities of these diffracted beams, we can determine the lattice spacing, crystal symmetry, and identify the material's phase. Every crystalline material produces a unique diffraction pattern. Essentially, it's a structural fingerprint. The peak positions reveal the unit cell dimensions, while peak intensities relate to atomic arrangement and preferred orientation. Broadened peaks can indicate a small crystallite size or internal strain, both of which are common in nanomaterials. Because the X-ray wavelength is about 1 angstrom, it is comparable to interatomic spacings. XRD bridges atomic scale, periodicity, and microscopic measurements. It is non-destructive, highly reproducible, and forms the foundation for almost every subsequent technique in structural analysis. The most common XRD measurement is the theta to theta scan, used for both powders and thin films. In this geometry, the sample is rotated by an angle theta, while the detector simultaneously moves by 2 theta, ensuring that Bragg's condition is satisfied for specific crystal planes. Each diffraction peak corresponds to a distinct set of lattice planes identified by their mirror indices H, K, L. The peak position tells us the interplanar spacing via Bragg's law, and from those spacings we can deduce the lattice parameter and even identify the crystal structure, whether it is cubic, hexagonal, or tetragonal. The intensity of each peak carries information about how atoms are arranged within the unit cell and whether certain orientations are preferred. In polycrystalline films, strong peaks in specific directions indicate texture or preferred orientation. The width of the peaks is equally informative. Broader peaks often arise from very small crystallites or lattice strain. Through models such as Shearer equation or Williamson-Hall analysis, we can estimate crystallite size and distinguish between size broadening and strain effects. Thus, a single XRD pattern encodes multiple layers of structural information: geometry, symmetry, orientation, and nanoscale strain. Another important aspect of interpreting an XRD pattern is understanding what the broadening of diffraction peaks tells us about the material. When the peaks becomes noticeably wider, it is often an indication of very small crystallite size or the presence of lattice strain in the sample. To estimate crystallite size, we commonly use the Shearer equation, which relates the crystalline dimension to wavelength of the X-ray, the peak width at half maximum, and a shape factor. A larger full width half maximum corresponds to a smaller crystallite size, so this simple relationship provides a first order estimate of nanoscale dimensions. However, peak broadening is not caused by size alone. Many materials also exhibit microstrain, smaller distortions within the crystal lattice, which contribute to broadening in a different way. The Williamson-Hall method is particularly useful here because it allows us to separate the contributions from crystallite size and lattice strain by analyzing several diffraction peaks simultaneously. These tools give us insight into the nanoscale structure of materials, helping us quantify how large the crystallites are and how much internal distortion they contain, both of which play crucial roles in determining mechanical, electrical, and optical properties. When we analyze thin films or epitaxial layers, conventional theta to theta scans provide only out-of-plane lattice information. Because these films are often oriented or strained relative to the substrate, additional scan geometries are required to obtain a full structural picture. The omega scan, also known as the rocking curve, measures the distribution of crystallite tilt around the Bragg condition. A narrow rocking curve indicates high crystalline quality and well-aligned lattice planes, while broadening signifies mosaic spread or misorientation. The phi scan is used to probe in-plane rotational symmetry. By rotating the sample around its surface normal, we can confirm epitaxial relationships. For example, detecting 4-fold symmetry in cubic films or 6-fold in hexagonal structures. The psi scan tilts the sample away from the diffraction plane to evaluate the residual stress or texture components not visible in standard geometry. Finally, reciprocal space mapping provides a 2D representation of both in-plane and out-of-plane lattice spacings, revealing whether the film is strained, relaxed, or partially coherent with the substrate. These advanced scans transform XRD from a simple face identification tool into a high-precision probe of crystalline perfection and epitaxy. While diffraction techniques like XRD average information from billions of atoms, electron microscopy gives us a direct, real space view of materials down to individual atomic columns. Because electrons have extremely short wavelengths, on the order of a few thousandths of a nanometer, they can resolve structure at the atomic level. As the electron beam interacts with the specimen, it produces a variety of signals: secondary electrons and backscatter electrons in SEM, transmitted and diffracted electrons in TEM, and even X-rays used for compositional analysis through EDEX. In a scanning electron microscopy, SEM, the beam is raster scanned across the surface and emitted electrons are collected to form an image of the sample's topography. In a transmission electron microscope, TEM, electrons pass through an ultra-thin foil, typically less than 100 nanometers thick, and the transmitted and diffracted beams form interference pattern, revealing atomic arrangement, lattice fringes, and defects. By combining SEM and TEM, we obtain a continuous imaging hierarchy, from micrometer scale grains to atomic scale defects, making electron microscopy the workhorse of modern nanoscience. The scanning electron microscope is one of the most versatile tools for examining the surface morphology of nanostructural materials. In SEM, a finely focused beam of high-energy electrons scans the sample surface in a raster pattern. As the electrons interact with the atoms in the material, they generate multiple signals, of which the secondary and backscattered electrons are most important for imaging. Secondary electrons originate from the top few nanometers of the surface and provide high-resolution topographic contrast, revealing surface features such as edges, steps, and roughness with exceptional clarity. Backscatter electrons emerge from deeper regions, and their intensity depends on the atomic number. Heavier elements scatter electrons more strongly and appear brighter, producing compositional contrast. Because of its relatively large depth of field, SEM produces images where even rough or uneven surfaces appear in focus, giving a distinctive three-dimensional appearance. Beyond imaging, SEM can also serve as an analytical platform. Detectors for X-rays, EDEX, electron backscatter diffraction (EBSD), or cathodoluminescence can be integrated to obtain compositional and crystallographic information from the same region. Together, these capabilities make SEM a powerful bridge between optical microscopy and transmission electron microscopy, offering both signal resolution and compositional insight across a wide range of materials. When a focused electron beam strikes a solid, it penetrates the surface and scatters through a small teardrop-shaped region known as the interaction volume. The size of this volume depends on both the beam energy and the atomic number of the material. High energy electrons or lighter elements produce deeper penetration, while lower energies confine interactions to the near surface region. From this volume emerge several important signals that together define SEM contrast. Secondary electrons originate within the top few nanometers and escape easily, revealing fine topographic details, edges, steps, and roughness. Backscattered electrons arise from deeper scattering events. Their intensity scales with atomic number, producing compositional or Z contrast where heavier elements appear brighter. Some inelastic collisions excite inner shell electrons, causing X-ray emission, characteristic of specific elements. This forms the basis of energy dispersive X-ray spectroscopy, EDEX, which provides elemental analysis from a few micrometer depth. A fraction of these excitations relax via a different route, Auger transitions, that emit electrons instead of X-rays. These Auger electrons have discrete energies unique to each element but come only from the outermost 1 to 5 nanometers of the surface, making Auger electron spectroscopy one of the most surface-sensitive analytical signals. Together, SE, BSE, EDEX, and Auger electron spectroscopy cover a remarkable range of information, from morphology and composition to surface chemistry, showing how SEM serves as both an imaging and an analytical platform for nanoscale materials. If SEM reveals the surface, transmission electron microscopy TEM reveals the interior. A high-energy electron beam, typically 200 to 300 keV, is transmitted through an ultra-thin sample, usually less than 100 nanometers thick. As electrons pass through the specimen, they are scattered both elastically and inelastically by the atomic lattice. The objective lens forms an image from these transmitted electrons, converting diffraction information into real space contrast. In bright field mode, the transmitted beam is used to form the image. Regions that diffract strongly appear dark. Dark field mode instead uses one of the diffracted beams, so specific crystal orientations or faces appear bright. By placing a small aperture in the back focal plane, we can isolate diffraction from a single region and record a selected area electron diffraction SAET pattern. This provides local crystallographic information, essentially a miniature XRD from an individual grain. At higher magnifications, high resolution TEM, HRTEM pushes the resolution below 0.1 nanometers, allowing us to visualize lattice fringes, interfaces, and defects such as dislocations or stacking faults. Contrast in TEM arises from multiple mechanisms: diffraction contrast, mass thickness contrast, where thicker or heavier regions appear darker, and phase contrast in high-resolution TEM images. Together, these imaging modes make a TEM a powerful bridge between atomic structure and microstructure, directly connecting synthesis with defect evolution and interface coherence. Each imaging or diffraction mode in TEM provides a distinct type of information, and their real power lies in combining them. Selected area electron diffraction (SAED) allows us to extract lattice parameters, orientation relationships, and strain in specific regions of a sample. It helps distinguish between single crystal and polycrystalline structures and between epitaxially and randomly oriented films. Bright and dark field images provide morphological context, showing grain boundaries, twin domains, precipitates, or dislocation networks. These modes are particularly useful for correlating crystallographic contrast with microstructural features. High-resolution TEM zooms in further, resolving atomic planes and defects directly. It allows us to measure interplanar spacings, visualize interfaces or stacking faults, and even perform Fourier analysis to quantify strain at the atomic scale. In scanning TEM, STEM, the high-angle annular dark field HAADF detector captures Z-contrast images where heavier elements appear brighter. This provides elemental and structural mapping at the atomic level, often complemented by EDEX or EELS signals for full compositional analysis. Together, these complementary modes bridge the gap between structure, defects, and chemistry, allowing a comprehensive understanding of nanomaterials across scales. TEM imaging demands samples that are extremely thin, typically less than 100 nanometers, so that electrons can transmit through them. The process usually begins with mechanical thinning, where bulk specimens are ground and polished down to a few micrometers. The goal here is to approach electron transparency without introducing scratches or strain. Next comes ion milling, where a beam of argon ions gently sputters away any material. As milling continues, a small perforation forms, creating an electron transparent window near the edge of the hole. For targeted analysis, such as a device interface, grain boundary, or nanopillar, researchers used focused ion beam FIB lift out. A dual beam SEM FIB system allows cutting, extracting, and mounting a thin lamella precisely from the desired location. However, each technique introduces potential artifacts. Ion bombardment can amorphize the surface or implant gallium ions, while hydrocarbon contamination may polymerize under the electron beam, producing spurious dark spots. Low energy final polishing and plasma cleaning help remove this damaged layer and surface residues. Ultimately, sample preparation is as critical as imaging itself. A poor sample can easily mimic non-existent defects. Always interpret TEM images with awareness of possible artifacts, and where possible, corroborate findings with complementary SEM cross-sections or AFM topography. Unlike electron microscopes that rely on energetic beams, atomic force microscopy measures nanoscale surfaces through mechanical interaction. A sharp tip, typically less than 10 nanometers in radius, is mounted on a flexible microcantilever. As the tip scans across the surface, interatomic forces such as van der Waals, electrostatic, or capillary interactions cause minute deflections of the cantilever. A laser beam reflected from the cantilever onto a split photodiode detects these deflections with sub-nanometer precision. The feedback system keeps the deflection constant, converting it into a height map that represents surface topography in 3 dimensions. AFM operates in several modes, each optimized for different materials. In contact mode, the tip maintains a constant repulsive force with the surface. Excellent for hard, flat samples, but potentially damaging for soft films. In tapping mode, the cantilever oscillates near resonance, touching the surface intermittently. This greatly reduces friction and deformation, making it the most widely used mode for polymers, biomaterials, and thin coatings. In non-contact mode, the tip never touches the surface. Instead, it detects attractive van der Waals forces through shifts in oscillation frequency, enabling non-destructive imaging even in air. The resulting images can resolve atomic steps, grain morphology, and roughness with a vertical precision of about 0.1 nanometer. Moreover, by analyzing force distance curves, AFM can measure mechanical properties such as adhesion, stiffness, and elastic modulus. Specialized probes extend its capability, allowing magnetic, electrical, or chemical mapping, making AFM a versatile platform for surface and functional characterization. Atomic force microscopy goes far beyond simply generating height maps. While topography provides surface morphology and roughness information, AFM can also map local physical and chemical properties through several specialized modes. In its simplest form, AFM computes average RA and root mean square RQ roughness, matrices often used to assess smoothness in thin film deposition or polishing processes. Phase imaging records the phase lag between the cantilever's drive and response in tapping mode. This phase lag reveals variations in viscoelasticity, adhesion, or surface chemistry, allowing different materials in a composite to be distinguished without labeling. Another capability is force distance spectroscopy, where cantilever deflection is plotted against tip sample separation. From these curves, we can extract adhesion forces, elastic modulus via the Hertz model, or even binding energies in biomolecular systems. Several AFM variants extend its functionality further. Conductive AFM, CAFM, measures current flow through nanostructures, providing spatially resolved conductivity maps. Magnetic force microscopy, MFM, uses magnetic tips to image domain structures and magnetic interactions. Kelvin probe force microscopy measures surface potential and work function variations with millivolt sensitivity, valuable for semiconductor and photovoltaic materials. By combining these data channels, AFM yields multidimensional data sets that link morphology, mechanics, and electronic behavior. For instance, mapping conductivity alongside roughness can distinguish grain boundaries from bulk grains in polycrystalline films. In this way, AFM serves as a cornerstone of quantitative nanoscale metrology, bridging imaging with local property measurement across disciplines. The Scanning Tunneling Microscope (STM), developed in 1981, was the first instrument to achieve true atomic scale imaging, and it relies on quantum mechanics rather than mechanical forces. When a conductive tip approaches within about a nanometer of a conductive sample and a small bias voltage is applied, electrons can tunnel through the vacuum barrier separating them. The tunneling current follows an exponential dependence on the tip sample distance. Current is proportional to exponential of minus 2kd, where k depends on the work function of the material. This means that even a 0.1 angstrom change in tip position can double the tunneling current, giving STM its remarkable sensitivity. In constant current mode, a feedback loop adjusts the tip height to maintain constant current as the tip scans. The height adjustments create a topographic map of the surface with sub-angstrom precision. In constant height mode, the tip height remains fixed and the variations in current reflect local electronic states, a mode particularly useful for flat, clean surfaces. Because tunneling current is governed by the local density of electronic states, LDOS, STM provides not only atomic topography but also electronic information. By recording the dI versus dV spectrum, we can map energy-resolved electronic structure, analogous to probing the local band structure of the material. STM requires extremely clean, atomically flat and conductive samples, typically metals or doped semiconductors, operated under high vacuum or inert gas to prevent contamination. Historically, the first STM images of the silicon 111 7x7 surface in 1983 transformed surface science, and later atom manipulation experiments like spelling out IBM using xenon atoms showed quantum level control over matter. Once atomic scale imaging was established, researchers quickly realized that the STM tip could do far more than trace surface topography. Because tunneling current depends sensitively on the local electronic density of states, recording the differential conductance dI over dV as a function of the bias voltage turns the STM into a local spectrometer. This provides energy-resolved information, for instance, mapping the spatial variation of electronic bands, surface states, or impurity levels. By collecting dI versus dV data at each pixel, one constructs LDOS maps revealing nanoscale inhomogeneities, such as dopant distributions in semiconductors or gap variations in superconductors. The same atomic scale control that makes imaging possible also enables atom manipulation. Famous experiments used the STM tip to physically push or reposition atoms on metal surfaces, spelling out IBM with xenon atoms, demonstrating quantum precision in matter control. In superconducting materials, STM can visualize the vortex lattice that forms under magnetic fields, while spin polarized STM, SPSTM, uses magnetic tips to resolve spin textures and magnetic domains atom by atom. Altogether, these advanced STM modes unify structural, electronic and magnetic characterization, a capability unmatched by any other microscopy technique. To summarize, each characterization technique probes materials through a distinct physical interaction, whether using X-rays, electrons, photons, or atomic forces. XRD reveals average atomic order, phase, and strain, ideal for identifying crystal structure and orientation, but offers no local morphology. SEM provides real space surface imaging at 1 to 5 nanometer resolution, showing grain size and composition, though limited to near surface regions and often requiring conductive coatings. TEM achieves atomic scale resolution, imaging defects, dislocations, and interfaces in thin foils, linking microstructure to properties but requiring complex preparation. AFM maps 3D topography and mechanical properties with sub-nanometer precision, without the need for conductivity or vacuum, but over small, slow scan areas. STM extends into the quantum regime, resolving atomic lattices and electronic states on ultra-clean conductive surfaces. Together, these methods span bulk to atomic scales, forming a complete hierarchy that connects structure, chemistry, and function in nanomaterials.